Okay, thank you. Okay. Yeah. Does it make sense what I say? Maybe you can't straight away change, but please make sense of what I say first, and then try to change. Okay. Solve by understanding instead of method. No, at the back. Okay or no? Okay. What I said is very important, please. Yeah. Yeah, solve by argument, don't solve by method. Okay, solve by argument. If your argument makes sense, then it works. Okay, let's do some tutorial question. So find the first three non-zero terms in the Maclaurin series for tangent x. Okay. So solve by argument. Last time, what did we learn? Okay, what did we learn? We learned the Taylor formula, okay, where you need to compute the n derivative and then compute n derivative at the point that you want to expand the series. Okay, so Maclaurin series expand at what point? S equal to 0. Okay, so you could use the traditional way, find the derivative and then compute the n derivative evaluated at s equal to 0. Or there's another way we use. Anyone remember? We can use the series that we have studied before. Okay. So for example, what kind of series we studied before? Okay. We studied at least 7 of them last lecture. 1 over 1 minus x, ln 1 plus x, tangent inverse x, ex, sin x, cos x, 1 plus x to the power k, binomial series. Okay. So we can use what we have learned before and then create a new infinite series. Okay. Yeah. So if your next question is why we can do that, then you need to figure out why. Okay. At least we produce this two way to find an infinite series or Taylor series for a function. Okay, so maybe I let you spend about 5 minutes and try which one you want to use. Let's find this Maclaurin series for tangent x. If you get stuck, you can try ask the friend beside you if or she or he can help you. So Maclaurin series is Taylor series at is equal to 0. Okay, try compute for 5 minutes, then we will compare answer. You guys still computing or we finish? Still computing? Anyone of you already done? Not yet? Okay, let's discuss. So, what have you tried? What have you guys tried? Sine over cosine. Okay, one of you try sine over cosine. What about the rest? The rest also the same or different? What did you try? You use derivative of tangent x. Is it hard to compute or not? Not hard. So how you compute the derivative for tangent? Already know? What do you mean? You mean right now is secant square. So you need to do up to 3 times, is it? Yeah. Okay. You do need to do up to 3 times. Okay. Sure. How about the rest? Any different method? Any different method? Also the same. Okay. So two classic ways. So we will make use for me. So we will try to make use from what we have computed before. So maybe I start from cos over sine x. Sine over cos x, sorry. Okay. So because sine, remember that sine x, the infinite series for sine x and cos x converges for all x. Okay, so it's kind of a good choice just to use them. So what's cos x? So cos x is what's sine x? Sine x is an odd odd function, right? So what you have are all the odd power of the polynomial, and then you need to put appropriate coefficient in front of them. Okay, so this is how you remember the infinite series for sine x. How you remember the infinite series for cos x? Cos is an even function. Okay, so only even power exists. So you got 1 minus x squared over 2 factorial plus x4 over 24 factorial. And then so on. Okay, there's an alternating sign here. All right. So what to do? You got two long polynomial, so you can do long division. Do long division to see what's the first three term. Okay, so to do long division, you just multiply x first to get rid of the x term. Then you are left with s cubed over 3 minus x5 over 30. You try and compute. Then you keep going, so you multiply by s cubed over 3. And then you get SQ over 3 plus or minus C should be minus because plus minus minus, so you get x5 over 6. Okay, then you keep going, left with 2x5 over 15, and then the third term you need is 2x5 over 15. Is this what you get if you do the derivative? You need to do up to 5th term, right? Isn't it? Because it asks for first 3 non-zero term. Okay, non-zero doesn't include the 0 term. So if you do the traditional way, you need to expand up to the 5th derivative to see this 3 non-zero term. You do all that. Okay. Yeah. So you need to differentiate 5 times in order to see this 3 non-zero term if you want to use the original formula here. Okay. So it's always often it's useful to use what you have computed before. Okay. Any question? No. Okay, so what's the radius of convergence for this Maclaurin series? What's the radius of convergence? The radius of convergence. What's the radius of convergence? I think should be true for all x. Yeah, I think should be true for all x. Should be true for all x. Hello. No response. Yeah, question. Yeah. What do you mean by pi? Radius? You mean around pi? You mean just around pi? Is it? You mean because of this, is it? Is this what you get? So is it pi or everywhere? You mean this pi interval, is it? Pi interval? Right. Is that what you mean? So do you just get convergence within this interval? Or no? Let me write out minus pi. Okay, and then I think we repeat this pattern, right, for tangent. Okay, yeah. So you mean at the end point it doesn't converge? Is it? Is this what you meant? Yeah, good question. Yeah, try and think about it. What's the radius of convergence? Okay. Yeah, let's think about it. What's the radius of convergence of 10x? Okay, so we will resume this question next week. Okay, try to think about what's the radius of conversion. Is it pi or everywhere? Okay, is it pi or everywhere? So we'll come back to this question again next lecture. Okay, so always when you do power series, infinite series, right? try think about the radius of conversion. Okay, don't just substitute and then do whatever you want. Okay, try and think about, does it make sense to substitute or not? Okay, after you substitute, what does it mean? Okay. Okay. Is it okay for everyone? Any other question? So the question is whether the radius of conversion is the pi interval or anywhere. Okay. Yep. Okay, let's go on. I mean, we will come back to this next lecture. But in the meantime, please think about it. Okay. So about the next one. Approximate the function fx, which is cube root of x by a Taylor polynomial of degree 2a equals to 8. Okay. So what does this mean? Any idea what does this mean? What does this mean? You compute T1, I mean T0, T1, and T2. Okay, constant, and then power 1 and power 2, degree 2. Okay, at the point 8. Okay, yeah, let's try and do this. Let's try and compute this. Okay, anyone computed the derivative yet? What's the first derivative for cube root of x? Hmm? Say, I cannot hear you. Anyone? What's the first derivative of cube root of x? Mm-hmm. Or how about the second derivative? Maybe from the other person this time. What's the second derivative? About this side, this side here, the back, from the back. What's the second derivative? Okay, good. Okay, so what's the next step? You want to evaluate this derivative at 8, right? Okay, so okay, f8 is easy, so it's 2. Okay, so what's f prime 8? Maybe someone from the second row here. Second, yeah. Huh? 1/2? 1/2? Yeah, okay, good. How about someone from the back of this row? What is second derivative evaluated at 8? Someone from the back? Huh? What do you guys get? Huh? Minus 1/. Say again? 144. Okay. 144. Good. Okay. So these are the second derivative evaluated at 8. Okay. But remember last time, don't forget to divide by the appropriate n factorial. Okay. So when you write out the Taylor polynomial, please don't forget the extra coefficient. So you got 2 plus 1/2 12 times x minus 8 minus 1/144 times 2, okay, times x minus 8 to the power 2. Okay. So the next question is how accurate is this approximation when x is in between 7 and 9? Okay. So what's this? How accurate is this? Or what's this question asking? How accurate is this approximation? Rn. What about Rn? You mean the remainder, right? So what about the remainder? What about the remainder? X minus T2. Okay. Is the remainder sure? Yeah. So what do you want to do with this remainder? Hmm? Yeah. Yeah. Remainder is the right direction to think about. So what do you want to do with this remainder? Ah, use Taylor inequality. Okay, use Taylor inequality. So why do you want to use Taylor inequality? Hmm. Okay. Okay. But both methods, what are they doing? They're doing. So what are you trying to do? I mean, eh, you don't tell me what you want to do. You just tell me what to do. Do Taylor remainder series Taylor formula. Right. So why do we want to use this? Yeah, we want to find the error. We want to estimate the error. Okay. We want to see how much left. Okay. What's the remainder? Right. Right. We only estimate until degree 2. We can still go on so that we can get as close as possible to our function cube root x. Right. So the next question is asking you, if I estimate until degree 2, what's the bound of my error? Okay. So how far am I away from the real number? Okay. So we want to find the bound. So to find the bound, what tool do we have? Okay, like what's your name again? I forgot. 榕树, 文树, 文硕, okay. So Wensuo says, because if we started with alternating series, we have a formula which is x minus xn bounded by bn plus 1. Okay, but in this case, this is not really alternating series. Okay, but we still can bound our error term. Okay, so the way to bound the error term is the Taylor inequality. Remember last time we used this to show that two Taylor series, Taylor series is equal to the original function. Okay, to show the limit of the remainder term going to 0. Okay, so that's why we're using the 2 here. Okay, and so what's the Taylor's inequality says? So Taylor's inequality says what? Okay. So in this case, which remainder we want to bound? We have degree up to 2, right? So we have remainder 2, which is defined by fx minus t2. Okay, we want to bound this. So what's the Taylor inequality we got? So we have R2x is less than equal to sum m over 3 factorial times x to the 8 power 3. Okay. And m is the thing that bound the third derivative. If you are not not familiar to this inequality, you should go back to the general form. Okay, see how we substitute this number. See how we apply this Taylor's inequality. Okay, if you can't understand, you should voice up. Okay, so how? And remember, this x is in between 7 and 9. Okay. Remember that for Taylor's inequality, we need to bound our x with a d first. Yeah, we need to have a bound for d. In this case, we bound it by 1. Okay, it's 1 away from 8. Okay. Maybe should I bring out the general form for you guys to refer, or you can refer yourself? Your choice. You guys want me to bring out the general form? Yes? Okay. Yeah. So let me bring out this general form. Okay, so one important thing when you talk to any mathematician, when we talk about a subject, right? When we say there's a Taylor inequalities, okay? In your mind, you should pop up this Taylor inequality, okay? Otherwise, this means you don't know what I'm talking about, okay? So when I talk about Taylor inequalities, you should have this appearing in your mind first, okay? If you don't know, then you should straight away ask, so what's Taylor inequality? Okay. After you know this, then next line will be apparent. Okay, let's see how to use this theorem. Oh yeah, the theorem here. So just now we decided we want to bound R2. Okay, we want to bound R2. So this means you need to apply this remainder to R when n equals to 2. Okay, when n is equal to 2. So if you want to bound R2, the condition here is you need to bound the n plus 1 derivative. So in this case, we need to bound the 2 plus 1 derivative, which is the third derivative. Make sense? Okay. But so far, we still don't know how to bound it yet. Okay, we don't know how to bound it, but we want to bound it by a number m. Okay, so the strategy now is to find the m, right? Okay. So also this the third derivative is bounded by m for x for some interval of x. Okay. In this case, our a is what is our a in this case? 8. Okay, our a is 8. How about d? Is it given or not in this question? What is d? 1, right? Because we want to care about x from 7 to 9. Okay, and then the series is centered at 8. Okay, so we got all these things already, but we don't have m. Okay, we don't have m. So how? So how? How to find it? M is related to the third derivative. Okay, so let's try and write out what is the third derivative because we already computed, right? Have we? Or we not yet? So we need to do it. So what's the third derivative? Let's write down first. We want to compute the third derivative. So what's the third derivative here? Where I haven't answered. Okay, how about first row front part? What's the third derivative? Anyone? Anyone? What's the third derivative? Okay, and then 8/3, right? Okay, good. So can we all bound this? What's x minus 8/3? This function diverges, right? When x equal to 0, approaching to 0, isn't it? Right. So how is it bounded? How is this function bounded? Can we bound it or not? Can we bound this thing? Is it possible to bound it? What other information you have? Yeah. So x is in between 7 and 9. X is a finite interval. Okay. So finite interval. And how can we bound this function here? How to bound this function here? Okay, so let me write down first. So we know that x is in between 7 and 9. Okay. So within 7 and 9, is this function continuous? Continuous, right? Okay. So have you guys learned what extreme value theorem? Something like that. So if it is continuous function on a finite interval, you can find a maximum. So how to find maximum? How to find maximum? Again, derivative y. I want to find maximum. Oh, you mean second derivative, is it? Okay, sure. So you say just second derivative test and then find the point where it is 0 and then check whether it's maximum or minimum. Is it? Okay. You could do it that way, but you should observe that this function is what? Increasing or decreasing? Decreasing. Decreasing on that interval. Okay. So if the function is decreasing on that interval, where is the maximum? At the starting point, which is x equals 7. Yeah. So this whole term here is bounded by 10/27, and then evaluate s at 7. Okay. And then if you press calculator, you get some super small decimal. Okay. So if you don't care about this decimal, this fraction is really your m. Okay? So you found the bound. So what's next? So by what does this theorem say? The remainder is smaller by this amount divided by 3 factorial. Okay. So in the end, what do we have? R2 is less than m over, okay, don't put m again, just put a real number in. So 0.0020655 over 3 factorial times 1. Yeah, times 1 cube. If you want, you can go into the decimal again. Why is it 1 here? Why is it 1 here? Is wait. Okay, there's some subtlety here. Okay, there's some subtlety here. So, okay, let me back up a bit. So let's back up a bit. So let's back up a bit. Precise. Okay, so let's back up a bit. So, the formula says that this remainder is less than equal to m over 3 factorial times x minus 8, the absolute value to the power cube. Okay. So x is in between 7 and 9. So everything in between 7 and 9. Right? 7.5, 8.5, 8.01. Okay? But we know that what? We know that x minus 8 is always less than equal to 1. Okay? So at most you can go away from 8 is 7 or 9. Okay? In between are all less than 1. So what? So we can bound the x minus 8 by 1. Okay? Absolute value of x minus 8.1. Why we put absolute? Any idea? Why do we put absolute value here? Why do we put absolute value? They are not for fun one. There's a reason why they put absolute value. So I think you are indirectly answering the question. You're indirectly answering the question. So keep going. So why we put absolute value here? Yeah, why we put absolute value? Say again. Okay, we don't want to get a negative value. We just care about the distance from 8. We don't care whether it's left or right. Okay. And then also, we only care about the real remainder. Okay. I mean the positive remainder. We don't care about whether it's too many or too less. We just care about how far is it from the actual value. Okay. So we only care about how far is it actually from the actual value. We don't care whether we are too few or too much. Okay, makes sense. So usually when you see this absolute value, right? Typically we don't care about left, right. We don't care about the direction. We only care about how much. Okay. So this is a general idea. Okay. Any question? Okay. So you can see that 2 questions we spend about 1 hour to do it. So it's quite time consuming when you do this tutorial question. But still, please do tutorial question at home. Okay. Yeah. For those like assigned one, I mean, if you can do all those, I think you are quite on top of your head already, on top of the material if you do all those. But yeah, to do really, really well, then you need to work really, really hard. Okay. Yeah. So maybe let's take a break until 12:06, and then we will start new chapter or series. I think there's an extra question here we will left as a homework. Remember one of yours name. Who is Liu Yuwei? Liu Yuwei. Oh, yeah, Liu Yuwei. Okay, okay. How about Sheldon? Who is Sheldon? Who is Sheldon? Huh? Who is Sheldon? Friends. Sheldon got no friend. Who is Sheldon? Friend. Yeah. Sheldon not here. Sheldon. Anyone know Sheldon? Where's he? Don't know. Okay. Never mind. Just asking. Can I ask who among all of you who are not Chinese or Malaysian? Can I see how many of you? Only two of you? International student? I mean, not international, I mean not from China or Malaysia. Okay. So you guys are minority. So the rest, please treat them well. You got minority friends here. How about among the Malaysian? How many of you coming from UEC? Okay, how many of you are Malaysian? Can I see how many of you are Malaysian? And then how many of you are coming from UEC? About half, about half, is it? Okay. If you are not coming from UEC, what stream you come from? And then foundation. Ah, I see. Okay. The thing I scare about UEC and the Chinese is because you need to change your language, right? Because you learn everything in Chinese before. So you need to switch to English. Correct.
First question, right? So you have to prove that the recursive formula is actually will have an explicit formula, something like this, right? So one, you get this formula. So if I use strong inductions, that what I did was since n is greater than 2, therefore the base case is n equals 3. Okay, here we get 1 plus 1 equals 2. And then for this one, we also plug in 3. So deal with the differential and then get 2 as well. And then here can I say it's true for therefore 1, 2, and 3? So it's just only true for machine.
I mean, the base case start from n equals to 3.
Base case is
Base case start from n equals to 3. Yeah, base case start from n equals to 3.
yeah, and then since
This is true for n equals to 1 and 2 because you define.
define
Yeah, because of definition, not because of induction.
Okay. So then strong induction would be something like this.
Why you need strong induction?
Because if you wanted to deal with recursion, right, I think we need to define, right?
Why induction does it?
Is induction enough?
I think this is true for everything below it. Then you should be able to use strong induction. I forgot what's the statement already, but yeah, I think. Do you really think strong induction? I'm not sure, but
So if this one was just assume true for n equals
yeah, I think just induction would be enough. Right? Yeah, I get what you mean already. What you say, meaning for every.
yeah, because if I were to use, because I don't have the formula for k minus 1.
So let's say you assume it's true for. Oh, right. Yep. Yeah, correct.
So I have to use this one, right?
Correct.
So basically after
Correct.
that,
Otherwise, you just yep.
and then because I stated it is 1, therefore it can improve on.
I mean,
Because 1 and 2 are different.
1 and 2 are defined not by strong induction, but I mean, there's a few ways to understand this sentence. I mean, how to say? So first of all, you can understand this sentence as this is true.
For n greater than 3.
I mean, but okay, the logic is n equals greater than 3 is true because by strong induction, but 1 and 2 is true by definition. So maybe you can ask, why is this true? I know that n equals to 1 and n equals to 2 is true, but how about n equals to 3 and above? Then you say by strong induction. Okay. This is just some, yeah.
And for this question, one is what I did was I said that
I think we should start soon.
okay, sure.
Yeah. Hello. So testing. Okay, I'll pass the this. Silent. Yeah, I think this binomial series, right? I think quite fascinating. If any one of you want to prove the whole thing, will be good. So write everything out in details. Okay. So the general case for this is k is a complex number. Yeah, try and work this thing out. I think it's very good. It'll be very good for everyone. If anyone can write out in detail for this one. Okay. Yeah. Yeah. So far, we don't really care about the interval of convergence, but it's a good exercise if you want to do. For this tangent x, right, we'll decide the phase next week. Okay. Next. So next we'll continue with Fourier series. So it's exactly like what is mentioned here. Why we continue Taylor's Fourier series is just because in power series we express the function in terms of polynomial, power of polynomial. But now we want to change basis. We change basis to to infinite series of cosine and sine. Okay, it turns out that power of cosine and power of sine is enough to express every not I doesn't mean express, but I mean approximate. Okay, approximate a function. Okay, sometimes it's not exactly equal, but it's a very good approximation. Okay, at least for some interval. Maybe not for whole function, but some interval is very good. So what's the definition of Fourier series? So Fourier series is an infinite series designed to represent general periodic function. Okay, so when your function is periodic, then typically you can find the Fourier series easily. Okay, so how does we use this sine and cosine way? So for example, if we play around with these two sine and cosine, depend on how you see it. Okay, so you can see that the period here is faster, here is longer. Okay, so when they are, so what's this line? What's this line here? So I guess this line are 0, 1, -1. Okay, otherwise doesn't make much sense. So positive, negative. Okay, so if you add positive, negative together, you will get some cancellation. So if you cancel out each other, you might get something like this. Okay, so if you get two constructive wave, then you will increase your amplitude. Okay, yeah. So this is how to take. So this is taking linear combination of function. Okay, so you take the sum of two functions, you get another function. Okay, so in principle, how to add two functions together? How to add two functions together? How to plus? It's a function. How to plus? For example, fx equal to x, fx equal to x squared. How to add two functions? Yeah, how to add two functions? Huh? Pretty sure you learned it before, but you didn't think it that way. So let's define fx equal to x, gx equal to x squared. So how to add two functions together? To add two functions together. How to add two functions together? Don't know. Huh? Huh? Any idea? Again? Remove the negative function. What? To the left. Why? Why? Why do you want to move G? I just want to add them together. So why do you want to move G? Okay, so you're saying that you mean we add these two together? Is it like this? Yeah, it is correct. Why? What are you doing actually? Yes. So you need to add it point wise. Okay, every point you add them up. So it's exactly what we did here. Okay, so every point we add them up. Every point we add them up. So we're adding the function point wise. Okay, so how to add two functions is actually adding them point wise. Okay, add function point wise. Okay, point by point we add, and then it turns out that if we add x and x squared together, it is just x plus x squared. Okay. Make sense? So you should start from what we know. We only know how to add number. Okay. But how to add function? We need to relate it back to how to add the number. So how to get number from function? You need to evaluate the function at every point, then the function will give you a number. Okay. Make sense? Does it make sense? Okay. So you add the function point-wise. So this is exactly what we did here. So every point at the same x, they have different value, we add them together, and then we get the new function. We call it f plus g. And this is a formal variable. We call it f plus g. Another new function. So this is a new function. Okay, new function. Why is it a function? Because if I give you an x, you give me a unique y. Okay, you give me an input, I give you a unique output. Okay, so this is the function. Make sense? Okay. Sounds very simple, but this is very important. Okay, this is very important. Please remember, this is very important. Okay, let's continue. So can we use sine wave to make a square wave? Okay. So sine wave is like this, right? Okay, so how to make a square wave? Okay, so let's start with a sine wave. Okay, so sine wave looks something like this, but it's not quite square yet. Okay, so it's still quite bumpy. So we need to reduce the bump. So maybe we add another term, which is sine 3x over x. Okay, and then you make it less bumpy, but you have more what? Wait. More, what do you call this? I forgot suddenly. I think we met this before in physics class. Can't remember the name. Okay. But anyway, we can add more terms. For example, sine 5x over 5, so that the wave kind of approaching the square. Okay, the square wave. Okay, then we can keep going on adding it. Okay, you can see that it is quite a what is kind of approximate the square curve, but with this a little bit small perturbation here. Okay, so this is similar to the principle of light. Although you see the light doesn't move, actually it moves to the frequency that you cannot see. Right? Okay, it keep turning on and off, on and off, on and off, on and off, until you can't see the difference. So you just link it to a what do I mean? Link it to a constant graph. Okay. So it just turn on and off until a stage that you cannot differentiate the difference. Okay, so this is how the light they make out the AC current. AC current. Yeah. Okay. So this is kind of similar argument here. Okay. So in this case, we'll have this formula for this approximating the square wave here. This is just an example. It's not some formal proof. It's just let you see the idea. Not formal proof. Just let you see the idea. Okay. So next, just how we say that Fourier series is an infinite series that designed to represent general periodic function. What's periodic function? Okay, you should ask what's periodic function. So periodic function is if you can found some positive p such that fsp equal to fx, then this is periodic. So period is p. Okay, so if you move x plus p, they're still the same. Move to x plus p, still the same. Okay, so this is periodic. Okay. So in particular, so sine, for example, so sine curve What's the period for sine curve? Huh? What's the period for sine curve? Huh? 2 pi. Okay? Because after 2 pi, you repeat again. Right? Let's check. So 0 and 2 pi is the same. And then pi, sorry, take pi over 2 and then compare with, what's this? 5 pi over 2. Okay, they are the same. Okay, they are the same here, they are the same here. And then you can continue to compare every point in between 0 and 2 pi, and then the point that after adding 2 pi to it. Okay, so this is a period 2 pi. Similarly, this sine function can extend backward, right? Can extend backward. Okay. You also can check that it's actually repeating 2 pi periodically. Right? Next. Yeah, so we covered this example just now. So let's see again. So 2 pi, 2 pi periodic for sine x, also 2 pi periodic for cos x. So you realize that actually cos x and sine x really not much difference, right? Okay, so if you move cos x backward, okay, maybe move by this length here, then you really get sine x again. Okay. Okay. So the difference between these two function is really about the initial condition. So meaning when you start at 0, which point you start first? Okay, one of them start at 1, the other start with 0. Okay, so the difference between sine s and cos s is just their initial condition. Okay. Yeah. Okay, so next. So we can change our sine, our variable inside our sine function and cos function. If we change by pi x over L, then the period will become 2L. Okay, you can check this, or you can just believe this. So this, for this chapter, right, it's just very brief, and then you will just learn some computation. So if you're interested, you can do research on it. Yeah, because this course is not on Fourier series, because Fourier series is quite a deep subject, actually. So in this course, we just learn some simple computation. Okay. So in particular, this topic, right, can be written as 2 project questions. So if you settle some technical problem in the first project, second project will have real life application. This first series there's a lot of real life application to Fourier series. Yeah. So this is one of the example that you can do for 2 projects under same content. Yeah. Yeah. We won't pursue deep in this topic. We just do some computation. Okay. In future, I think you guys will meet it again. I'm not sure what course, but you will meet it again. So okay. So yeah. Please remember that if I change the variable of sine and cos by pi x over lambda, it will give a periodic function with period 2 lambda, 2L. Okay, 2L. So next, so we start with function that define on minus L to L. Okay, so why we don't want to talk about 2 pi? Why we want to talk about L? Because we want to talk about general period. Okay, we want to talk about general period. Not only 2 pi, maybe we change to 2, change to 3, change to 4, or change to irrational number, anything. Okay, we just want to fix some period domain. So we call it minus L and L, right? Because we can always split the interval into half. Okay, so we can find this L. Yeah, and this is a convenient way to do it. Does it make sense? Does it make sense? Okay. Any interval, we can just split it in, and then we can find this L. Okay. So So we start with this setting here. So we have a function that defined on minus L to L. And then this f can be extended to be a periodic function on R. Okay, so what does it mean? So let's say you start with something non-periodic. Okay, maybe you start with something non-periodic. Maybe like this. Okay, on this interval here. Then you can make it a periodic. How to make it a periodic? How to make this periodic? Let's say I only have function non-zero between minus L and L. I make this periodic. Maybe I get some. Never mind. I just do this. Okay. You make this periodic. Okay. First of all, it's a function on minus L to L. Okay. How to make it periodic on R? So meaning over the whole real line. And how to see this as a periodic function? You make a periodic function. Is there a easy way to make a periodic function? Do you guys understand the question or not? Not understand? Not understand? Not understand? Okay. So let's repeat again. So let's say we got a function on minus L to L. Okay, so we look at one interval, maybe minus L here and L here. Okay, we got a function. Okay, can we extend this function or create a periodic function on R? Yeah, meaning over the whole real line, it is a periodic function. Okay, meaning the sign repeated pattern of the function. Can you do it? Do you get a question now? You get a question now? Uh, yeah. Does anyone get what he say? Again, what he say is just in a layman word is you just repeat this picture here again and again. Okay. Make fx equal to fx plus 2l. Okay. So you just repeat this in a easy language is you repeat this pattern forever. Okay. Extend forward, extend backward. Does it make sense? The answer. Okay. Any question from this row at the back? The back. See some confusing face. Question? Any question? No? Any question? I see some confusing face. Any question? No? Okay. Okay. So yeah. So extend just means there's one obvious way to extend it. You just repeat the function. Okay. So the definition of Fourier series of f is so how to read this? So you write the first term here is the constant term. Okay, maybe you will ask why there's a over 2 here since this is a constant. Might just as well write it as some B naught, W naught, Z naught, or so on. Okay, but first of all, just leave it as A naught over 2 first. And then second, there are linear combination of these are linear combination of different period of sine and cosine wave. Okay, so maybe you will ask, why not power of sine and cosine wave? I think there's a formula relating power of cosine and sine back to cos n pi n theta, right? So you can, you can re-express everything back to by changing the period of your sine and cosine. Okay. Next, next is how does this this coefficient come about, or how this a0 bn and a0 come about? So it can be derived that to find this a0, an, bn, actually you integrate over the interval, okay, and then you use your original f multiplied by corresponding period of cosine and sine wave. Okay, we won't do it here. Later we'll see what tool we're gonna use. Later we will also see example as an exercise. Okay. So this comment we made before, so this minus L and L, we can integrate over any alpha to beta interval. Okay, as long as it's 2L. We just rename the interval. So how to prove this, find this coefficient? Actually, we need to rely on this special cases. You can see that this integral is equal to 0. I think it's also a bit too much for me, kind of crazy. But what they use is really the cosine and sine formula. Okay, so you take a product of cosine, you can express it back to just cosine, the linear combination of cosine. And then from there, you can see that actually the integral cancels out. You can try it out. Not necessarily you can see it for the first time, but you can try it out. Also try the formula for product of sine b. Okay. Yeah. Then you can see that you can roughly see that let's say if you express your f in terms of this guy, right? So you have some cos and sine here. Okay. So how to find the coefficient here? You just take this multiplied by this cos or sine thing. So you can see that you will have product of cos or cos sine or sine or sine cos. Okay. And then when you match this thing together, this identity here will help you to cancel out some of the term. I mean, most of the term. Okay, you can see that if they don't agree, you can see that if m and n are distinct, if you have product of cos and a sine, they straight away go to 0. And those terms disappear. Okay. And then what else? If you have cos sine together for any non-negative integer, the product also go to 0. Okay, so these help you to cancel out most of the terms. Okay. And then what else? So if you have cos square with the same integer n, okay, then it will be equal to sum L. So you just so this simplify all your computation. So these special cases will help you to prove how you get A0, A, and B. Yeah. So if you can't imagine it, you first listen to what I say first, and then you can try it out yourself. Okay. Okay. Next theorem is Next one is, let's say f and f prime are piecewise continuous at the interested interval, okay? And then we want to find the Fourier series of f. So just now we know that we can express the Fourier series as the linear combination of cosine and sine wave of different period. But this Fourier series also converges to half of the limit of fx from the right and the left of s0. Okay. Yeah, so these two equal. Okay, so what does this imply? Okay, later we'll see example. Okay, we will see example later. So don't be worried. We'll look at example soon. What does this mean exactly? Okay. So let's do example. So next example is this. So we have this example here. So let's consider a function. We have a function which is 0 from -1 to 0, and then 1 from 0 to 1 inclusively. Okay. So let me ask you a question. Is this a periodic function? Yeah. Is this periodic? So let us draw this out. So what's this? So it is from -1 to 0, it is 0. And then from 0 to 1, it is 1. So all the way from 0 to 1. Okay. So is this periodic? No, right? Okay. So we can make this periodic by setting fx plus 2 is fx. So meaning we copy this diagram and then paste and then extend forward and backward. Okay. So in this case here, if you plot out the graph, it will be something like this. Okay. This is just from -3 to 3. So you can do it from -4 or -6, -5. Yeah. And then you can make it longer actually. It's just repeating. Okay. So next question is find the Fourier series of the function. Okay, how to find the Fourier series of the function? So let us bring the formula out. So let's remove this. Okay, so we need to find the Fourier series of the function. Okay. In particular, we need to find all the a0, an, and am. Okay. So we don't know how this formula come about, but let's try and use this formula first. Let's see what they give. So what should we do? What should we do? So first, okay, see from this definition here, we need to determine our L first. What is our L in this case? What is our L? 1. 1 is it? 1, right? So our L, so we need to determine what is our L first. So minus L to L is -1 to 1. Okay. Okay, so what's A0 here? Okay, A0 is 1 over L integrate from -L to L fx dx. So how to integrate from -1 to 1 of fx dx here? How to integrate this function? Second, the area. Sure. Okay. You can straight away see from the area Or you can see that -1, okay, this function is a piecewise function, right? Okay, so you could integrate it piecewise. So from 0, 1, 0 to -1 to 0 is 0 dx, plus 0 to 1 is 1 dx. Okay, which is which is 1. Okay, so a0 is 1. Okay. How about an? So an, you also do the same integration, right? But in this case, you have extra coefficient popping up. Of course, pi x over L, which is 1 in this case, dx. Alright. So similarly, you also split into two piecewise parts. Okay. On the part from -1 to 0, it is just 0. Okay. So really what you get is from 0 to 1 cos n pi x dx. Okay. So do we know how to integrate this? What do we get if we integrate cos n pi x? We get sine n pi x over n pi. So in the end, we get sine n pi is what's sine n pi? 1, huh? 0, right? So our sine go to 0 at every pi, right? 1 pi, 2 pi, 3 pi, 4 pi, 6 pi, negative pi, all go to 0. Okay. Yeah, so we get 0. Let's do another. Haven't finished calculate yet. We have to do bn. How about bn? It's the same, but replacing cos with sine. So we get cos n pi x. I think there's a minus, right? Do we have a minus? Over n pi to 0. Okay, what do we get? One? Not 1. 1 over n pi, not quite. Okay, wait, I got 1 over n pi. Huh? Don't think so. Maybe let's write it down. What is it? So what is cos minus cos n pi over n pi plus 0? So you got 1 over n. So what's this? What is 1 minus cos n pi over n? How does cos behave on pi? Just bring the diagram up. Right? It is 0. It is when it is 0. When it is 1, it's 0. When it is pi, it is -1. When it is 2 pi, it is 1. And then 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Okay. So depend on the n. Okay, depend on n. So how does it depend on n? How does it depend on n? So when it is 0, it is 1. When it is pi, 1 pi, it is -1. When it is 2 pi, it is 1. When it's 3 pi, it is -1. 4 pi, 1. 5 pi, -1. N plus 1. So where do you start your n first? We start our n with 1. Let's start off n with 1. So we just put, is it enough? Yeah. If we start our n with 1, then we put n. Okay? We start our n with 1. Okay. Okay, so put everything together, what do we get? What do we get? What do we get? Let's put everything together. The formula for the Fourier series is as such. Okay, so we got our A1, A0, sorry, to be 1. So it's 1/2 plus, what is AN? We found that AN is always 0. So we kill the cosine wave. But we have an alternating on and off sine wave, which is 1 minus 1 to n. Okay. So it turns out that we only use sine pi to approximate it. Okay. Which kind of makes sense, right? Kind of makes sense, right? Because your sine start here and then go down, go up. So if you can cancel out this part here, then you're left with this part. Okay. Okay. Seems like you guys are quite tired. Maybe we continue next time. So I have an office hour today. So if you want to come, please come. For either for assignment or for project or for general course content. Okay.